So here we have an optimization problem. Imagine there is a wall outside a house. The wall is 8 meters high and 4 meters from the house. We need to find the length of the shortest ladder that will reach the house when one end rests on the ground outside the wall. So to illustrate the problem, we should draw a diagram and label any known values. Since we are minimizing the length of the ladder, we should represent it with a variable. For now, we'll use the letter L. Then let's isolate the parts of the diagram that are useful to solve the problem. We can split the triangle formed by the ladder and the house into two right-angled triangles and a rectangle. The angle the ladder makes with the ground can be represented with the variable A. The angle that the ladder makes with the wall will be the same because the angles are made from the same straight line and from horizontal lines that are parallel to each other. To solve for optimization problems like this one, you have to express the value you want to maximize in terms of only one variable. Since we are dealing with right-angled triangles, we can use SOHCAHTOA to find an expression for the length of the ladder in terms of the side lengths and the angle the ladder makes with the ground. For the lower section, we can use 8 over sine A, and for the upper section, we can use 4 over cos A. The length of the ladder can be expressed as the sum of the segments of the ladder we just found. So to help you understand the boundaries of this problem, I made something in Desmos that will help you visualize the situation. Alright, so here's a graphical representation of the problem. As the angle of the ladder changes, you can see that at some point the ladder reaches the shortest length it can possibly be. This is the angle we are trying to find. However, when the angle of the ladder gets really small, the ladder gets really long as a result. Eventually, if the angle becomes 0, the ladder will be infinitely long horizontally. The same thing happens as the angle approaches 90. The length of the ladder approaches infinity in the vertical direction. And it makes sense if we look back at our equation. If we sub in 0 or 90, either sine A or cos A will be 0, and this makes the equation undefined. So this means that the angle must be in between 0 and 90 degrees. So now we have a function for the length of the ladder in terms of the angle of the ladder to the ground. All we need to do now is find an angle between 0 and 90 that will make for the shortest length of ladder needed to reach the house. Before we go on, you need to understand the concept of a derivative. All a derivative is a function that represents the instantaneous rate of change at any point on the original function it was derived from. Basically, it gives you the slope of the tangent line at any point on the graph. One type of notation for a derivative is, for example, you've already seen the notation of a function written like f at x equals 1/2 x squared plus 1. To represent the derivative of this function, all we need to do is attach a prime symbol on the function like this, and we get f prime at x equals x. So now if we take a look at f at x and its derivative on two different axes, we can draw a line that only touches f at x at the point where x equals 1. If we want to find the slope of the line, then we can use the slope formula. We can use the point where the line touches the graph and the line's y-intercept. We can find the slope and see that the slope of the line will be 1. If we take a look at the graph of the derivative on the right, we can see that when x equals 1, the derivative equals 1, which is the exact slope of the tangent line at x equals 1. This shows that we can use the derivative to find the slope at any x value. This also works in reverse. We can also use it to find the x values that have a known slope. So we can use this to find the x values where the slope is equal to 0. The derivative has an x-intercept at x equals 0, so that means the original graph will have a horizontal tangent at x equals 0, which is exactly what we can see in this case. You should also notice that the graph is at the lowest value it can be when it has a horizontal tangent, so we can say that the minimum point on the graph is when the derivative is equal to 0. There are other cases where this could mean that the graph is a local maximum or minimum or a point of inflection, but we won't go into those for this video. So how do we even find the derivative in the first place? Well, there are a few rules we can use to quickly find the derivative of most functions. One of them is the power rule, which is when you only have one variable raised to an exponent. In this case, we'll just use n as the exponent. To take the derivative of this, we need to move the n in front of the variable and decrease the exponent by 1. So for example, the function that we looked at before was 1/2 x squared plus 1, and we can use the power rule to find the derivative of this function. I should note that when you use the power rule on a constant value with no variable, you get 0, since the constant value just represents a horizontal line on a graph, which always has a slope of 0. So to find the derivative, we take the exponent and move it down to the front of the x and decrease the 2 by 1. The 1/2 and 2 cancel out, so then we are left with f prime at x equals x. Another example could be 1 over x. First, we can express this term with exponents. We can move the x from the denominator by raising it to the power of -1, because when you have a negative exponent, it means that you have to take the reciprocal of the term, and the reciprocal of x is 1 over x. We do the same thing we did in the first example to take the derivative. We move the -1 in front of the x, and then we decrease the exponent by 1, so -1 becomes -2. Then we should simplify and get rid of the negative exponents. So then we get -1 over x squared as our derivative. Another rule we need to know is the chain rule. It's used to take the derivative of composite functions like h at x equals f at g at x. To find the derivative of this, we need to first take the derivative of the outside function while keeping the inside function the same. Then we multiply the whole thing by the derivative of the inside function. For example, if we wanted to take the derivative of a function like h at x equals 2x plus 3 to the power of 4, we could say that f at x is x to the power of 4 and g at x is 2x plus 3, and then we could rewrite h at x as a composite function. So we can use chain rule to take the derivative of this. We first take the derivative of the outside function by moving the 4 from the exponent down to the front of the expression and decreasing the exponent by 1. Remember that we keep the inside function the same. Then we have to multiply this by the derivative of the inside, so we take the derivative of 2x plus 3. When we simplify this, we get 8 times 2x plus 3 to the power of 3. The derivative of trigonometric ratios of sin x and cos x are simpler. All you need to know is that the derivative of sin x is cos x, and the derivative of cos x is just negative sin x. For this video, we won't go into the proofs for these rules, because we just don't have enough time. So going back to the original function we created, we now have enough information to find the derivative of the function. First, we should remove the fractions by raising the terms in the denominator to the power of -1. Now we can take the derivative of this function. We have to use chain rule on both the terms of this function, because sin x is raised to the power of -1, it can be seen as a composite function. So if you remember, we just bring down the -1 and lower the exponent by 1, so it becomes -2. Then we have to multiply the function by the derivative of the inside function, sin a. The derivative of sin a is just cos a, so we just multiply it by cos a. The other part of the equation is the same. We bring down the -1 and the exponent becomes -2. Then we multiply by the derivative of cos a, which is negative sin a. Simplifying this, by getting rid of the negative exponents, we get -8 cos a over sin squared a plus 4 sin a over cos squared a. Now we can find the maximum or minimum points by setting the derivative equal to 0. So when we set it equal to 0, it allows us to move over -8 cos a over sin squared a to the other side of the equation. Then we're allowed to cross multiply the denominators from each side, and we get 8 cos cubed a equals 4 sin cubed a. Then we can divide both sides by 4 and cos cubed a. This simplifies to 2 equals sin cubed a over cos cubed a. We can take the cube root of both sides, and we can use the trig identity of sin a over cos a equals tangent a. So we can sub in tan a. Then by taking the inverse tangent of both sides, we can find that the angle that gives us the max or min is 51.56 degrees. To find out if the angle gives a maximum or minimum value, we can check the boundary cases. The boundaries in this case would be 0 and 90, since the angle cannot be less than or greater than 90 degrees. So we can check values close to the edge of our boundaries. First, we'll sub in 1 into the original function, and we get 462.39 meters for the length of the ladder. Then we can sub in the angle we found, which was 51.56 degrees, which will make the ladder 16.65 meters long. Finally, we can sub in 89, and we will get 237.2 meters for the length of the ladder. So we can see from this that the angle we found does in fact give us the minimum length of the ladder. We can say that therefore the shortest length of the ladder that can be used is 16.65 meters.